Hello all, I am Rajasree Angel, roll number 76. Now let's see how filtering in frequency domain is done. Generally, frequency domain filters are different from spatial domain filters as it basically focuses on the frequency of the images. It involves convolution operation. But when we perform filtering in frequency domain, it simplifies to multiplication. Therefore, for fast and easy computations, we prefer performing the filtering operation in frequency domain. Now let's see how padding is done in frequency domain filter. Firstly, construct a frequency domain filter as the same size of the image. After that, compute the inverse discrete Fourier transform of the frequency domain filter to get a spatial domain filter. Now pad the spatial domain filter and then convert it back into frequency domain by computing the discrete Fourier transform. Here we can observe that there are 6 images. In this figure, the first 3 images shows the frequency domain filters. The next 3 images shows the corresponding filtered images obtained. This complete image is obtained after computing discrete Fourier transform of the third image, and this image shows the height of the filter itself is 1. The first image is a blurred image and the second image is obtained after multiplying the phase angle and computing inverse discrete Fourier transform. Third image is the original image of a blown integrate circuit. And then the low frequencies in the transform are related to slowly varying intensity components in an image, such as the wall of a room or a cloudless sky in an outdoor scene. On the other hand, the high frequencies are caused by sharp transitions in the intensity, such as edges and noise. Therefore, we would expect that a filter h of u, v that attenuates high frequencies while passing low frequencies, appropriately called as low-pass filter, would blur an image, while a filter with the opposite property called as high-pass filter. Now let's see the MATLAB code of this to clearly understand these images. Let's take the image and is labeled as F. F is the blown integrate circuit image, and we took the Fourier transform of that using MATLAB's FFT2. We want to work with double precision, so that gives us a transform that is the same size as the original image but of complex type. So let's view that just for visualization, and we'll take the log to enhance small values and take the absolute values of those complex numbers, and then we will shift the transform so that the zero frequency is in the middle, so that will be the Fourier transform of the image, the circuit here. Now we filter it with a box filter of size 20 by 20. So we will create a filter in that size n by n, and we will normalize it so that the total is equal to 1. We had to pad so that the result now is only 20 by 20, but we want it to be the same size as our input image. So we need to pad it by assigning the point in the lower right hand corner to be a 0. Taking the fast Fourier transform of the filter is capital H just for visualization, and we get the Fourier transform of the filter. Now we have took the inverse Fourier transform of D2 of capital G, so that we will get a blurry version of the input image as a result. And these are the results for the MATLAB code implementation. In this, the figure A shows a simple image, and the figure B is the result of blurring with a Gaussian low-pass filter without padding, and figure C is the result of low-pass filtering with padding. We are comparing the light area of the vertical edges in figure B and figure C. Now let us see the MATLAB code of this to clearly understand these images. We shall be getting the image script here, so for that purpose we assign the capital A to code with image data, and we use the syntax IamRead. We should provide the input image, that is image.jpg here, After this particular image has been taken as input, we shall be assigning the dimensions to the variables m and n here with the syntax size a. Further, we require a certain filter mask for the low pass filtering purpose. So we use the variable mask and that shall be working for the image sample. Initially, we use the mask as a matrix of zeros and the dimension should be same as that of the image sample. Initially, we have given the dimensions m and n so that the mask should be of the same dimension. The mask we have to specify for low pass filtering before we have the mask of some portion of whiteness and some portion of blackness. With the help of for loop, we can specify the low pass filter cutoff frequencies here. So for loop, the first variable shall be I here and here we provided the range 150 to 180. Then for the next for loop, we have another parameter j and it is having 210 to 240 here. Now we have applied mask with dimensions I and j with the value 1. As the method is for image enhancement into the frequency domain, we get image data and mask data shifted to the frequency domain. For that purpose, we have took another variable c and we have used a 50 shift here and provided the input mask. Next variable is b and we have used a 52 as input. Now d shall be holding the coefficient to coefficient multiplication of these transformed ones. So we can have the b dot multiplication with that of the c parameter. We have another resulted variable to hold the data back to spatial domain, so that is e here. So for that purpose we have used the absolute value after IF52, that will be the inverse transformation, and that the image is d after multiplication of the two transform matrices. Now the task is to display the results. Here we have used subplot command. Under subplot we are having 2 comma 2 comma 1. Here we assigned I am show command. At first it will be the original image which is to be processed by the low pass filtering and have given a title here, that is original image. Next the subplot 2 comma 2 comma 2 here. For display purpose, we require ImShow command. We change the data type as unit 8 and the resultant is holded by E here and the title is low pass filtered image. The third subplot is 2 comma 2 comma 3 and here we can show in mask for the low pass filtering here and we gave the title as low pass filter mask. Finally, the last subplot 2 comma 2 comma 4, it will be again the command I'm show and we give C here, that is after a 50 shift operation. Now we have the results displayed. This is the low pass filtered image by utilizing this particular mask. After a 50 shift, the mask will be represented at these four corners here. And these are the following results for the MATLAB code implementation. The spatial frequency domain is a technique to separate the effects of scattering and absorption consequently for a quantity and a set of chromophores, convolving the spatial representation of the blurring filter with this image. When the filter is passing through the top of the dashed image, it will encompass part of the image and also part of the bottom of the periodic image right above it. When a dark and a light region reside under the filter, the result is a mid-gray blurred output. However, this filter is passing through the top right side of the image. The filter will encompass only light areas in the image and its right neighbor. The average of a constant is the same constant, so filtering will have no effect in this area giving the result. It involves a filter that can be specified either in the spatial or in frequency domain, and padding is done in the spatial domain. The relationship between spatial padding and the filters specified directly in the frequency domain. Now let us see the MATLAB code for this to clearly understand these images. I am read an input image and converting it to grayscale image if it is a color image. The first portion, the size of this image and storing in m and n. Why? Because we need to take n by 2 liter m. assigning some cutoff frequency. So this cutoff frequency depends on the pixels. If the image is 200 plus 200 pixels, then take the half of that, there is an 100 and divided by 2. Now we have used the Fourier transform of this image by using FFT, that is two-dimensional FFT, and supporting the Fourier transform of the input image without shifting the location of subblocks. Here we have only plotted the absolute part of A, and that is the real part of it. There will be shifting the origin by using FFT and again taking the real part of this to insert this plot, and this will show the Fourier transform of the input image after shifting. Here we have used a variable for storing low pass image. For u is equal to 1 to m and for v is equal to 1 to n, where u and v are coordinates of the image. D of uv is equal to square root of u minus m by 2 whole square plus v minus n by 2 whole square. If d of uv is less than or equal to 0 as per the formula of ideal low pass filter, we have to put the pixels as it is during below as well as the filter will be 1 if it is less than d0, but if it is more than d0 then the pixels will be rejected as it is 0, and also the filter will not be having any value that is 0, it will become black. After ending the loops, we brought in the ideal low pass filter FIIT. Now let's see how it looks on the surface plot also, so that we will be doing using the surface plot. So we can use mesh for showing the surface plot. Now we have shifted our image initially. So again we will be shifting the origin of the filter debates, and after reshifting we will be taking the inverse Fourier transform to return back to spatial domain. And we will be subplotting the filtered image in the last portion of subplots. And these are the results for MATLAB code implementation. From this example, we can see that failure to pad an image can lead to erroneous results. The purpose of filtering is only for rough visual analysis. The padding step is skipped sometimes. From this, we conclude that a filter can be specified either in spatial or in frequency domain. Thank you.